All right. We can go ahead and get started, and then people will trickle in. So today we're going to go over transient non-homogeneous problems, specifically using Green's function. So the goal for this class, it's up there, but really by the end of class we want to get to the bottom one, which is at least solving 1D problems using Green's function. And if you can solve 1D problems, doing 3D or 2D is going to be very similar formula. So, I want to start with a little warm-up. If you want to talk to your neighbors, which hopefully most of you like the people in here. All right, we've got a problem here. It's a 1D plane wall with a heat generation term that varies in the x direction and with time, and along with two time-dependent boundary conditions. So, you can discuss with me or with your neighbors. What would you do to go about solving this? Or based on what we've done so far, what issues would you foresee?
Hello. You got a lot of non-homogeneous.
You got to use superposition.
Yeah. You get complex time if T infinity is not zero. You have heat generation. One steady state and one non-steady state. You don't have transient resolution. Which you get to.
Right.
For the steady state, you have to divide that.
You have to split it.
Two is given.
Time generation.
One generation and one non.
You can't split that generation term.
Do you think you can solve it with what we have
You can't split the generation term and the time.
Where they have like heat,
Okay,
zero, and there's like temperature, or X.
And then
Okay.
maybe
We won't get there today, but I'll come up in the future.
when is it when T goes in T or X goes in when T goes in?
Not semi-infinite, no. I
I
said 1D. I'll write it down if that's going to help you. But just from 0 is less than X is less than O. All right. I've heard most people stop talking. Who thinks we can solve this right now? Who thinks we can't solve this right now? Who didn't raise their hand? Okay. All right. Why don't you think we can solve it right now? You think you can solve it?
I think it's solvable. I didn't say I can solve it.
That's why I asked, can you solve it?
Yeah, I can.
All right. Savannah.
Is it because your heat flux and your convection depend on time?
Yes.
We haven't dealt with before.
Right. We haven't dealt with that before, right? So these can't exactly just get our eigenfunctions like we have before. So that's what Green's function today is going to take care of for us. So I've got a definition. It's right off of Google. And it says that Green's function is an impulse response in a non-homogeneous linear operator defined on a domain with specific initial and boundary conditions. You do not need to write that down. And it probably sounds like a jumbled mess. But essentially what we're looking at here is we want to still have, a temperature that's varying with r, or our position vector, and time. But now we're going to add in a generation term that's a function of both space and time, as well as account for a storage term. This is all going to be within some domain of r cubed, or real numbers for our space condition, and then typically we're going to look at real times, or at least time greater than 0. Okay, so we will start with defining some specific or generic boundary conditions, which we've done this quite a bit before, so hopefully it's all feeling familiar. And again, as with last lecture, feel free to just shout out if I'm writing. If you have a question, you don't have to wait for me to look for your hand. So we'll have some for a Fourier's law for our conduction plus some sort of potential convection term, and that will correspond to our, oh, I'm writing this wrong already, some sort of convection term. Right, so these can all be time dependent. We're going to define this entire heat flux as just some function on I, which I is going to correspond to some surface I. So on the previous page, right, we had two surfaces, one on either side. That's what our I is going to be, right? Then we'll also define some generic initial condition. It's going to be T in the entire region at time equals 0. It's equal to some function in terms of our position vector. Okay, this feel familiar for everybody so far? Good. All right. We're also going to define these things called the Dirac delta functions, which Dr. Loutzenhiser has put these up along with the proof for the Fourier integrals on the Canvas announcement. Did you all see that? Okay, great. So we're going to define these Dirac delta functions, which is also just going to be called a unit impulse. And for people that love differential equations, this should feel rather familiar. So these are going to be some generalized function over real numbers that has very specific properties. So we're going to use the variable lowercase delta, and where x does not equal 0, it's going to equal 0. And then across an integral from negative infinity to infinity of delta dx, this is going to equal 1. Okay, people remember this from diff EQ? Something similar? Nods, thumbs down, thumbs up? Somewhat? Okay. Essentially, what this is going to allow us to do is to turn on and off different functions. So let's say that I have this integral from negative infinity to infinity of this f of x times delta of x minus a dx. What do we think this could be equal to? Yeah?
Question, this is equal to f of a. But question, delta x is not equal to 0, is equal to 0, and delta x is equal to 0 is equal to 1.
Sort of. But it's defined based on the integral. So it's not just a point at 1 exactly.
Okay. So anything but x equals 0 is 0?
Yes.
But when you add 0, it's 1. So it turns off all points except...
Correct. So I don't know if everybody heard, but Fadi did say that this would be equal to f at a. And so essentially what we've done here is we've turned off every single point for this function that's not at x equals a.
This is kind of like how we've been applying the orthogonality for previous functions.
Not quite. We're going to use this to define a general function today, and next lecture this will actually get applied. We're going to still do some, we'll get to that next step. Dr. Loutzenhiser?
You do that for the Fourier integrals. And so there's a proof of that on announcements.
Yeah. All right. So we are going to now take what we have here where we can turn on and off a point source or a time source, because we can do this with time as well. We're going to define this generic Green's function here. So we're going to say that g, will be our Green's function here, is going to equal 0 for any tau, which will be some arbitrary time that we'll talk about more, but any time less than t. And so this tau right here is representing what we're moving through in the system, and we're going to see that as an impulse. We're then going to substitute this in to populate our heat equation that we have generally. And so we're going to write del 2 of our Green's function in some real space and time based on an impulse, which is r prime and tau, plus 1 over our thermal conductivity times some delta function that is going to be displaced by r prime and shifted in time by tau is now going to equal our storage term as g instead of t. So right here, we have this is going to be our real domain, or also our effect, based on this impulse. So if we have some function here that's going to contribute to a point source or any type of source at this specific vector in space, r prime, and at this specific time, tau, right, that's going to now affect our value for g. It is going to correspond to our temperature. Question, Fadi?
So basically, this is like, let's say we have a temperature profile, and then we have a point where there's like a jump in temperature.
Yes, exactly.
Like a shock in temperature.
So I'm going to draw this out, and I copied this in my notes directly from the textbook, so you'll be able to see it. But if we have some sort of cube, right, and we're going to say all of these, for our purposes, are going to have homogeneous boundary conditions and some initial condition that's equal to 0. And then we might have right here, say, a point source, right? And this will be a point source at our r prime, and it might take effect at time equals tau. So this is what we're looking at. Some heat generation term that's specific in location and specific in time. And that's what our delta functions are going to allow us to turn on and off. So if we look at this in 3D, like I just showed up here, I'll write the stuff for 2D and 1D. This 3D is going to be a point source. If we consider this to be a 2D problem, it would be a line source. And if we consider this to be 1D, it will be plane source. And our units are going to change accordingly. So in 3D, we're going to be looking at Kelvin per joule. In 2D, we'll look at Kelvin meters per joule. And in 1D, we'll look at Kelvin meters squared per joule. So again, just to reiterate, so our G in real space, in real time, is going to be affected by some impulse at r prime and tau. So we can consider just, if we're defining this, G on the left side of this bar right here is going to be an effect, and the right side is going to be some impulse based on our delta functions. So some up here, some instantaneous point in time in a specific location, we're dumping heat or removing heat from the system. All right, thumbs up, thumbs down. How are we feeling? Good? All right. So now the question, how does this affect temperature? Right? That's just some fundamental theory. So we're going to start looking at Green's function and using it to actually solve a distribution in temperature. And the genius in this really is that once we know Green's function for any problem, based on the conditions, we can solve out the temperature distribution really easily. So our temperature in real space and time is going to be equal to, this is going to be a very large equation, but bear with me. So across some domain R prime will be our Green's function. Evaluated at tau equals 0 times some initial condition, R prime, or evaluated at R prime, differentiated over the entire volume, plus thermal diffusivity over thermal conductivity, integrated from the point we're releasing through time of that same Green's function times this generation term evaluated at our impulse space, integrated, oh, I missed something. This is also going to be integrated through all of space. So d tau and across our entire volume here, plus one last part, which is going to be alpha times the summation from, that's I equals 1 to n of this integral from tau equals 0 up to time through for any given surface of our Green's function times 1 over k times a certain boundary condition differentiated over the area and through time. Okay. That's a large equation, I know. This will be equation 8.6 in the textbook if you want to refer back to this later. I'll wait till everyone's done writing. Yes, Fadi.
The surface, Jake, can I ask you exactly what the surface, like, you said at the start, it's like basically, in a 1D, it's just like maybe the bottom, any surface you're looking at.
Sure.
That's basically it.
Yeah.
You need to sum all these surfaces and what's...
So I'm going to turn this around on you all. There's 3 terms here. Talk with your neighbor. And if you can define what each of these terms represents, write that down. Because that's what I planned for. Take a minute or two. No. You can discuss with me when you're done talking with Avery.
Because the lowercase g is each iteration.
You two don't want to talk to each other?
Oh, nice. Volumetric. Jumping in.
With respect to time.
You don't know? I said it while I was writing it down.
Oh, okay.
All right, think through. So, what's different between each of these?
Yeah. The first one seems to be an
Doesn't have time. Right, so if it doesn't have time, then it would be what? So, steady state, but think we're adding stuff to this. Instead, what's the opposite of steady state? So steady state's at the end. What's at the beginning? Right. Okay. Right. And see, that's why we have our capital F. Okay. Yep. And so then think in the next term, what's different? Generation, right? And in the last term, what's different? Exactly. Right. So those are our boundary conditions.
It's SI for a given surface.
Make sense? Great. Yes, Kari.
Okay, so we think we have it.
Yep.
First term, initial condition. Second term is heat generation with respect to temperature, time and third is summation of portions at the surface.
Yeah, exactly. Yes, Fadi.
The first term is the spatial term, no?
No. All right, we're going to bring it back. All right, this first term. All right, you three. What's different about the first term? There's a time, tau is equal to 0. So this is going to be our initial condition. You see that, Fadi? Okay. What's different about the second term? Generation, right? So that's easy. The second term is just going to be our generation. And the third one's probably the hardest. What's different about this?
This is the combination then of the storage term and the spatial term.
Not quite.
Some of this,
It is over area. Yep, and it's the sum of these surfaces, right? So this is f of I. And if I can bring us back to here, right, where we're defining our boundary conditions as some function, f of I, this is going to correspond to any non-homogeneous boundary conditions. Right. And so once we have this Green's function, g, then all we have to do is plug and play, right? We can just put in this integral, we can add our initial condition, we can add what our generation function is, and we can add our non-homogeneous boundary conditions here.
Where are the spatial conditions?
The spatial conditions.
Just generally, where's the spatial? They're in the non-homogeneous boundary condition.
So you mean like throughout space?
Yeah, like
Right, so that is in our Green's function right here.
all of them are okay.
All of them are going to have a function across space. All right, now a challenge for you all. Can you, if this is for 3D, can you write the version for 2D? I'll give you, say, 3 minutes. And work with your neighbor if you're stuck. Ask questions. Yep, exactly. You got it. I'm not going to walk across your cord. No, you're good. You're good. How are you doing? Daniel, right? Okay. We're still going to write it as R for this because we can still apply this to spherical. Is it all right? That's half of it. So the other is here. So if we were integrating over surfaces before, what would we integrate?
One surface. Each line.
Yeah, a line.
A line, but the lines are surface. Yeah, basically, I don't mean like surface. DS means like the length. So like the
You all right?
like the x.
Okay.
Right.
Right. What about the last term?
Not over SI. Or
Either X or Y.
Well, let's say, not necessarily X or Y. Let's think of it generically, because this could be cylindrical or spherical coordinates.
Yeah.
So, underneath an area, what would that be? Like the integral to get an area is the integral of a line. So, right, we're just going to replace those areas with lines. Yeah. So that's to show like a difference between them, and it's mainly for our integral purposes, right? So if we're integrating across area prime, means we're not going to take anything that's just a function of r, right? Does that make sense? Are you sure?
I'm not sure.
So, can I borrow your notebook for a sec? So, say you had an integral that was x times x prime dx prime, right? That's what this is. So, this x is not going to be changed at all. They're different variables, but they correspond to the same thing. Cool? It's that's our impulse domain. That's what we're turning on and off. All right. Who's got an answer for me?
Just drop everything down by a dimension.
Drop everything down by a dimension, right? So this v is going to become an a prime. This v will become an a prime. What's this a prime I going to be?
R, lowercase r.
Lowercase r? Yeah, lowercase r is, all right, I'll be a little confusing with these already. So we're going to use li prime. And then this here, we're going to use a lowercase li prime, right? So instead of, on these two, instead of integrating over a volume, we'll integrate over an area. And then for this, we'll integrate over lines. Make sense? All right. We're also going to have to deal with our non-homogeneous boundary conditions. So as before, we had K times our differential of temperature with respect to the norm is going to equal some surface heat flux is defined as Fi R of T. We've already done this a number of times before where we're taking this and making a corresponding homogeneous boundary condition for superposition. We're now going to say, for this case, dg dni is equaling 0. And then for a constant temperature, we're going to say G equals 0. And then the last one will be for convection. We're going to say 1 over K of G is equal to plus or minus H on that surface times our differential with respect to the norm. It'll be plus or minus based on what you've probably seen in the most recent homework, I think, based on if we're going in or out with our convection or based on how we're defining our coordinate system. Okay? Yep.
These are just for 2D?
This will be for everything.
This is for everything.
Yep. And our last little bit is I'll give you the equation for 1D. So it's slightly different. T, we're just going to call this x now because it's a little easier. It's going to be our integral over a line of g of x and t, and our impulse evaluated at t equals 0 times f of our impulse position. And we're going to add in this little x prime p dx prime. And I'll define that in just a second. And then we'll give our generation term from tau equals 0 to time along a surface g x prime, our impulse, times our generation, this constant again, that up again. That's I equals 1 up to n of our integral from time equals 0 to t of x p, our Green's function with our impulse, bless you, 1 over k, and then our boundary condition integrated across tau. Okay, so again, looks very similar, except we're introducing this xp, which is essentially our integration constant, or they'll call it in the book the Sturm-Liouville weight function. And so for this, if we have a slab, we're going to say P equals 0. For a cylinder, we'll say P equals 1. And for a sphere, we'll say P equals 2. This is just going to make sure we're integrating these values correctly for the coordinate systems.
But we still take x. So x is what? So in a sphere, isn't it r?
Yeah. So x is just a position vector still. It's not, I'm not restricting this to Cartesian. We're just using x as the position vector. And I'm doing this so when you look in the book, this will be equation 814. You're not scared because the variables are different. Okay. So now the question is, we have this Green's function, right? And if we know it, we can just solve for the temperature directly. How do we get Green's function? So that's what we're going to do now. We're going to, everybody have this page? Good? Okay. We're going to say, suppose we write our temperature from previous problems in such a form that it looks rather similar to the Green's function. So we're going to call it some function in r prime, and t times our initial condition, evaluate prime, dv prime. So whereas before you'd probably write down your temperature as something that's a summation, some term, integral of some term, differentiated through x, we're going to rewrite this like this. And this value k is what we're going to call the kernel, right? Our kernel of Green's function. So now if we take this, we compare, so here, let's say that, suppose now we have this integral of k in r prime, and time times f of r prime dv prime is equal to this top right here. So it's going to be equal to our Green's function at tau equals 0 times some initial condition dv prime. Right. So do you all see how if we choose to rewrite our temperature like this, we can now make this claim that we can set our temperatures equal to each other, assuming, right, we have no heat generation and homogeneous boundary conditions. So, right, we're going to follow these terms out. Or simply by stating this is just going to look at our initial condition with tau equals 0. Question? Why did we do that? It's a great question. Because now, if we take this, we can then say any temperature where we're solving with no heat gen and homogeneous boundary conditions, for those, this function k is equal to our Green's function evaluated at tau equals 0. Right? So now, if we can solve for k, we can then just plug that right into here, and we'll have our temperature. I'm seeing some blank stares. How do you solve for k? Well, we'll get there first in a second. But before I do that, I'm just going to make a note. This is t equals 0. We want this to just be in terms of t. So we can make a substitution, and I believe there's a proof in the textbook that if we say for t goes to t minus tau, then this will get rid of our tau equals 0. Okay. So you ask, how are we going to get the kernel? So I'm going to say, suppose that I gave you a temperature distribution, x, y, z, and time equals some summation and n, m, and p, some constant, sine of beta nx, sine eta my, sine mu pz times our exponential negative alpha lambda squared subscript nmp t times some integral of our initial condition integrated over that volume. Right. You've all seen an equation like this before. You hopefully solve for them on the exam. So what's our kernel here? If we're saying this is what we want our temperature distribution to look like, what can we get as our kernel down here? You can take a moment, talk with people next to each other. And the f of x? Anybody got a guess? Just 3 signs on the exponent. So taking this And this is going to be equal to k? We want the constant too? Is that it? And the summations. There we go. Right. So we rewrite this. We can say t of our x, y, z, and t. Let's bring this integral out, right? It's going to be our integral. I'm going to skip writing every little detail out because you have the function above. We'll have some constant, sine 1, a second sine, third sine, exponent, initial condition, dv prime. Right. If we're comparing here, let's cross out our initial function, or our initial condition, drop our integrals, right? And this is our kernel right here. That's our k. Everybody good? All right. We're doing great on time. Let's do an example. All right. So let's say I've got a 1D cylinder. That's defined from 0 up to b. And we're going to have some boundary condition that is a function of time now. At time is equal to 0. Our temperature is going to be equal to some function in the radius. And we're going to give it this heat generation term that's dependent on both r and time. Okay? So, let me write the steps out for you. So step 1 is going to be our problem formulation. So we'll start with our governing equation. So 1 over r, differential with respect to r, times r, differential of temperature with respect to r, plus 1 over k, our generation term, equals our storage term. We'll have 2 boundary conditions. The first one is going to be our temperature as r approaches 0 is finite. Our second is going to be this one that's listed right here. So our temperature at r equals b is equal to some function in time. And this, I wrote wrong. This is our initial condition. Will be our temperature at time equals 0 is equal to some function in r. Okay. Yep. Absolutely. That's why I'm writing it out, so you can keep pace. All right, good to move on? All right. Step 2. We want to define a homogeneous problem that's parallel to the one we had before. So I'm going to use psi for this because that's what the book does. We're going to say psi of r comma t. Oh, skipping a step, sorry. 1 over r d dr of r times our differential of psi is equal to 1 over alpha. I really hate writing psi dt, right? And since this is a homogeneous problem, we're dropping the generation term. that'll be non-homogeneous. Then our boundary conditions. So boundary condition 1 is going to be the same thing. So psi as r goes to 0 is still finite. But what about boundary condition 2? Yeah. So this is going to be equal to 0, right? Our homogeneous condition for that corresponding heat flux, or for that corresponding constant temperature, is just going to be a temperature of 0. And then our initial condition is going to remain the same as well, because Green's function is going to be independent of that initial condition. So we'll still have this f of r. Okay. Step 3, we're going to solve our homogeneous problem. And how do we solve this problem? What method do we use? Separation of variables, yes. Done it a million times before. So I'm going to go pretty quick through this because you've all done it before, but we're going to say psi of r and t is going to be equal to some function in the r direction and some function in the time direction. So we can implement that. As we go through these terms. I know normally we would use lambda as our separation constant here, but for whatever reason, the book on this problem uses beta. So I'm going to call this beta squared. Let's apply boundary, sorry, I'm skipping a step again. We're going to say gamma of t equals, what does it equal?
C1 exponential negative alpha beta squared.
You'll all talk at once, which I love to hear, because it means you know it. But it's also hard to listen. All right, and what's our function of r? C2. Yep, our Bessel function of the first kind of order 0, beta r, plus C3, Bessel function of the second kind of beta r. Okay. Then we can go ahead and apply boundary condition 1, which is that psi as r goes to 0 is finite. So if we apply that, what's going to go away? C3, because our Bessel function of the second kind of order 0 would go to minus infinity, exactly. So apply boundary condition 1. C3 goes to 0. And then if we apply our boundary condition 2, psi of r equals b is equal to 0. We're going to get a function for our eigenvalues, which is going to be j naught beta n b equals 0 for n equals 1 up to infinity. All right, and then we can go ahead and apply our initial condition, or actually, let me rewrite this function out fully first. So we're going to say psi is now equal to the summation across all solutions, n equals 1 to infinity, some constant Cn times j naught beta nr times our exponent term okay. Then we'll apply our initial condition, which is just going to be psi at time equals 0 is equal to f of r. So this will then equal that summation Cn J naught beta n r. What do we do here? Apply orthogonality. Great. So we're going to multiply by our integral from r prime equals 0 to b of r prime J naught beta m r prime dr prime. Since you all have done this before, I'm going to skip down past where we get what Cn is. I'm just going to write it out. Psi r comma t is going to be equal to 2 over b squared, the summation from n equals 1 to infinity of our exponent, negative alpha beta n squared t times j naught beta n r over j1 squared beta n b times our integral from r prime equals 0 to b r prime j naught, gosh, this is a long function, r prime f of r prime dr prime. Okay, we've all seen these solutions? All right. So now, step 4, reformulate. Again, just like before, we want to extract the kernel out of this. So we're going to write this now. This equals, we'll take our integral to the outside of 2 over b squared times our summation, exponent negative alpha beta n squared t, our Bessel functions, and our constant, r prime j naught beta n r prime f of r prime dr prime. Okay, so now can we extract the kernel from this? Okay, so what's going away?
Everything but integral f of r prime dr prime.
Yep, so we'll drop these for our kernel, and we'll drop the integral, which then is going to give us, if I can get this paper straight, k, or g, bless you, and r in time affected by our impulse and tau equals 0. Is equal to 2 over b squared, our summation, our exponent, negative alpha beta n squared t, times j naught beta n r, j naught beta n r prime, over j1 squared beta n b. All right. And then our step 5 is going to be just replacing t with t minus tau, so we can get our Green's function not at tau equals 0. So g of rt r prime, we're almost through it, equals 2 over b squared, the summation, which is now going to be the exponent of negative alpha beta n squared times t minus tau times this. There you go. We have our kernel. We have our Green's function. So then all that's left to do is just substitute. We're not going to do this to save a little bit of time. I fully believe in all of your abilities to do algebra, but we'll just substitute it back into equation 8.6, right? So you can plot the Green's function at tau equals 0 right here, add our initial condition, add our generation term in this one, add our non-homogeneous boundary conditions in this third term.
So just a faster way of solving
You couldn't solve it before? Right.
You could have solved it with like superposition. It would have taken ages.
You could not have solved this with superposition.
Because of the time? Yeah.
All right. Much like last time, I'm going to let y'all loose. So I'm going to give you another 1D problem. It's going to be a slab. It's almost like it's the problem from the beginning of class. It is the exact problem from the beginning of class. So we'll have a generation term. It's a function of position and time. At time equals 0, we'll have some, I wrote r, this should be x. We'll have some initial condition. On this side, we'll have a heat transfer coefficient and some time-dependent fluid temperature. And on this side, we'll have a heat flux that I'm going to call F1 of T. And this is going to be bound from 0 is less than x is less than L. So we've got, say, 13 minutes, maybe a little bit less. Work with your neighbors. Work through it. If you wrote all the steps down, you just follow the same steps. And I'll walk around and answer any questions. No, you're good. Great. It's all easy. You just follow the steps. They're all the same problem. Sorry?
F1's flux or temperature?
Flux. Yeah. Should be. Let me check that. Yeah, so this is going to allow us to solve for non-homogeneous transient problems. Whereas non-homogeneous transient conditions. Conditions, right? Whereas before, superposition allowed us to handle multiple non-homogeneities, but they weren't time dependent. Now we can handle time dependence. Yep. Upon what time did you enter in? Okay, you're fine. generation term? Yep, we're just looking at the homogeneous problem. We're just looking at getting the kernel, and then we can substitute it back into that equation earlier. Right. Yep. All what we want to find is just G, because then the rest is easy. Yeah, well, so with n, right, remember, what is this I in these, the surface, right? So for 1D, how many boundary conditions do we have? 2. And how many of them are non-homogeneous? Right. So then n is going to be 2. And so we'll have both. So, yep. So really, it's not really summation. I mean, it is, but like what you'd write is, you'd write this expression out for one boundary condition, and then you write it out for the second one. Yeah, so if you had a cube, you do it 6 times. Seems like a good problem for the project. How are you doing?
Yeah, that's agree.
Cool. Awesome. Write out the problem like you normally do. And then step 2 is to find a homogeneous problem. So right, we're going to drop the generation term, and we're going to convert all our boundary conditions that are non-homogeneous to a corresponding homogeneous condition.
That's great.
So a heat flux, right? So now, what would you set that equal to make it homogeneous? Instead of f of t. Yeah, exactly. In fact, we wrote this earlier down in the lecture, and I told you exactly what they'll change to. Before this problem, we went over it. Right before this, I think. Yep, so right there. Right at the bottom of your page. Those are going to be what we convert our boundary conditions to. Right, and so this one. You got it? Where are you at now? Nice, great. Right, because we haven't covered that before. Yeah. Right, okay, I'll mention that. I mean, you could do the linear or like product rule to solve that, but we don't cover product rule, do we? Yeah. Gosh, how are you doing? Mm-hmm. Okay. Yeah, exactly. All right, nice. You finished already? No. You're good. Where are you at? I had 10 minutes. Oh, okay. All right. Hmm. Absolutely. I mean, most of them are integrals you can't take, right, when we have a generic question. Yeah, of course. That'll be our homogeneous problem, just like superposition. That's the actual problem, which is T. So to get to T, we're just going to go back to this, right? So we've solved for G, and we can just substitute that in, and now we have T. So we solved for G in the example problem. And G's in each one of these terms. And you know what f of x is. And you know what G is. And you know what fi is, because those are all given in the problem. So then you just simply take G and put it in here. And there's your temperature.
So the final answer is T plus 5.
No. Phi is just what we're using to solve for G. Because we're going to set it up as a homogeneous problem in order to get G. That makes sense? Okay. Yep.
When we do reach this point, when we substitute back, you don't expect us to solve that Green's function.
I don't grade you. That's going to be my...
You think it's possible? It's not possible.
Okay, so generally with all of our questions in this class, we're not saying g of x and t is equal to some function. We're just saying you have a function. So how could you integrate it?
You want to integrate it?
No, I'm saying you can't integrate it.
You can.
Right. So you can write it as the generic form. Right. In the project, you'll have real numbers, and then you integrate it. But in the project, you'll also use MATLAB or Python or whatever system you want. All right, we're getting to the end of class. I just tell you, one, this is example 8.3 in the textbook. So if you didn't finish, it's written in every single step and you can look at it. This is going to be our final Green's function. We'll substitute it back into our Green's function equation in the book to get our temperature. Where were people getting stuck? Or if you weren't and this was just a time issue? Anybody? Stuck? You're all masters at this? All right. In that case, we have 5 minutes. I'll answer any questions, but in the meantime, there is a feedback form for me on Canvas, and if you can pull that out and respond, I'd appreciate that. Yeah, any questions, I'll just awkwardly stand here and wait for. Do not clap for me, please. No questions?
Where's the lambda n squared h squared plus h over n? Where do those terms come from?
Yeah, this.
That's the norm.
If you write out the eigen in terms of angles of the triangle, you can write it out.
You can look at it by doing the triangle method, or you can look at table 2-1. Or 2-1, 2-2, 2-3, 2-4. This will be Cartesian. This will be cylindrical. I think this one's also cylindrical. Yeah. Yeah.
When we wrote the original form with R vector and T for 3D case, why does that formulation hold?
What? Sorry?
The original formulation for writing
Yeah.
solution,
This.
why does this work?
Why does this work? A very famous mathematician that came up with Green's function and also the Gauss-Green theorem and other stuff in the early 1900s. If you really want to know, the book doesn't even go over it, but it lists references that tell you how it was derived. Oh yeah, smarter people than me figured that one out. Thank you.